when he plugs it in.
I think we may be recording, Mr. President. Are we on the air?
Yep, looks good.
Whoa! Well, hello, everybody, stargazers. You're on board the once-a-week online live vlog for Santa Barbara, California's longtime telescope and astronomy club, the Santa Barbara Astronomical Unit. Heard and seen Mondays, 11 a.m. till noon for an hour. We call it the SBAU Astro Hour. I'm your proud host, former radio host, now on vlog, on Zoom, Ron Herron, Vice President of the club. Will introduce you to the rest of the board and some very passionate members in a moment. Meantime, follow along on YouTube and be ready to comment or ask questions, would you? Because we got to tell you, these are some of the brightest, most knowledgeable folks around. Come join our club. Friday night, we got a big meeting up at the Santa Barbara Beautiful Museum of Natural History in Fleischman Auditorium. First Friday of every month, we get together. Second Saturday night, we have a star party, and there's some planetarium viewing involved too. Tell your friends, come join us, and doggone, let's do it. Let's talk about these items this week. This is program number 154 of the Astro Hour for January 29th, 2024 to February 4th. We're going to place the planets in the sky again, like we like to do, except for Pluto. Apparently, it's finally losing its respect. The last quarter moon will be toward the weekend this Friday when Dr. Tim Thompson talks about that Southern California mountain with the observatory on it. It's been there for a long time, Mount Wilson. We're going to visit the Queen, Cassiopeia, and the Princess, Andromeda. One's just a lowly constellation. The other's a whole galaxy, plus two of Andromeda's satellite galaxies. What's the winter hexagon? We're going to find out, and where it is. The largest telescope camera ever built, we're going to kick around. Wait till you see the size of this sucker. It's at Stanford. More on light cones. Oh my God. We add in 2 dimensions, 3 dimensions, 3D, even 4. Hope we don't lose you. Some of it's, some losers losing some of us, I got to tell you right now. However, let's meet the gang. Once again, continuing the presidency is Jerry Wilson.
Good morning.
Here we sort of lose track, don't we? Pat Forgy is his wife, great supporter and a great telescope man. We have Chuck McPartland, our SBAU outreach coordinator, who's married to merchandise manager and new treasurer, just elected, Pat McPartland. We have Tom Whittemore, editor of our incredible monthly newsletter. Only one on the screen who's not wearing glasses. His wife is Maureen. And he's retired from, but somehow doesn't miss his tenure at Westmont College as a science instructor. Bruce Murdoch, we did have on board.
There he is.
There's Bruce, longtime supporter, telescope enthusiast, president of the Santa Barbara Theater Organ Society. And we'll let him talk about it if they got something going on. His wife is Bonnie. And Lord Levaduck, look who's joined us permanently as we're heading toward our 4th year in March. Tim Crawford, resident lens and telescope expert, longtime member, and married to wife Karen. We always get these silly cartoons forwarded to us by President Jerry, and we have humor through the week, and I thought we'd like to share them with you, our little levity at the beginning of the Astro Hour. Mr. President, take off. I'll see if I can match some of the sillies you've sent to us here. On that one, I didn't get. It's a burger, including the French fries inside. There's a patty in there, but what the hell's the deal? Is it going to eat us? What did I miss?
You know, to me, that looks like the picture of Einstein where he's sticking his tongue out.
Yeah. Yeah. Right. Squint your eyes a little bit.
Yeah.
Okay. Albert Burger, that's why. Okay, got it. I should have got it from the title at the top.
See, I'm always a little bleary-eyed. So
yeah, the one where he's laughing, right, Chuck?
His tongue is sticking out.
I've seen it. I've seen it. How in the world did they get Einstein to do that? I don't know. Must have been a fun guy underneath. All right.
He had to paste all those French fries on his face, right?
A couple of Norwegian explorers arrive at the South Pole. The flat earthers are going to love this one because the one says, "We're here, Eric. Antarctica, bottom of the world." And Eric, of course, falls off into space because it's the bottom of the planet, I guess, right?
Well, there's no centrifugal force at the pole, but there's certainly gravity.
That's true. There is a little force there going.
No, it's pure fantasy. What does Disney call it? Believable, impossible, or something?
Here's another one that needs explaining to me. Do not remove, etc. It's one of those repeating imaginary number things like pi, or what are we talking about?
No, it's 0.8 and then threes forever.
Yeah, so it goes right through the wall.
And if you take the bar off that shorthand notation, then you have to write out all the threes.
And they go on
What is-
forever.
So
Yeah,
it is like pi. It's one of those imaginary
Yes.
repeating
it's an
not
numbers.
irrational
imaginary.
number.
No, it's a rational fraction. I mean, you can
It's rational.
5, 6, right? 5
Yeah,
divided by 6.
pi doesn't repeat.
No.
But I've never seen an equation that had a fraction on one side and a decimal point on the other. Can they both be in the same formula? I don't think they can they?
It's
Well,
just
they're-
two different
they're-
ways of representing a number, Ron.
Right. Yeah,
I
and
know, but-
all rational numbers, Ron, will repeat eventually. They will repeat.
I would think if you're using fractions on one side, you got to use it on the other. If it's all decimals, that's just a
No,
different
it's
way of
it's
saying
just a different way of representing a number.
Right.
I've never seen the bar. I've never seen that. Never mind. I
Never-
got it.
well, lots
You
of
might
things.
have,
If you,
you might have
if you
missed
look at
that day
the,
in math.
the decimal equivalent of 1/7 or 2/7, any of those,
So
that
this-
one repeats after, I don't know, 7 or 8 or 9 digits.
And you've never
Don't you put
seen,
three,
you know,
three
1 over
dots
2.
again too?
Yeah.
If you divide 6 into 5, then you start going with 0.83 da 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 forever and
Yeah.
goes through the
Forever.
wall.
Yeah.
I've never done that.
Haven't you ever seen 1 over 2 equals 0.5?
Yeah.
1 over 2 equals, well, of course.
Okay.
There's a different way.
And
the
one
same
one
thing.
seventh. Ron, one
Okay, well,
seventh.
let's get back to
one four,
rationality
1 4,
here.
1 4, 1 4.
Or just 1/3, you know?
Yes.
Okay, what do we got here? This is Jerry called this one grad school exam. This is a one ring distance on an exoplanet far, far away in a super intelligent extraterrestrial watching the American scientist, the professor, do tricks on the blackboard. That's abducted by an alien circus company. Professor Joe Doyle is forced to write calculus equations in the center ring. Hope you sent that to Joe.
I don't
All right,
remember if I did.
This is a couple of astronomers arguing in the shack next to a big radio telescope, arguing, half expecting someone with a blown up paper bag ready to pop it says, we seem to be picking up background radiation from two sources. Was there also a little bang?
Yeah,
There's nothing now. Here's the young man on the couch.
this is
Phoning up
unreal.
on his, phoning up on his mail account. When employers want 10 years experience before you turn 20, that's what you get. Doggone it. I don't know where you get these, but there's an endless supply of them, Jerry. It's amazing. And here it is, a brand new element on the periodic table, added to the period, the element of confusion, of course. Number 29. What is number 29? Does anybody know what it's?
I'm just looking it up. It's copper.
I was going to say it's a
Copper.
metal. It's got to be a
it's
metal.
copper.
Copper. Okay.
Because we have way over 100, but
They
like
should have put a 1 in front of the 29.
the last quarter on the table were founded by humans or made by humans, and they only last, what, a split second or something?
Some of them are very unstable, but there's supposed to be an island of stability out there farther that they're trying to reach.
Did most of you get the very last minute? Oh, here we go. I'll talk about that in a second. This is the Bluebird's got Wi-Fi, no need for a wire. Yeah, he has
Yeah.
Wi-Fi, therefore he's wireless. He's sitting in the space. I love it.
Pretty good.
There you go. And here we go. These are oh my God, we're on another planet.
Elon
And
Musk.
the extraterrestrial says, look here, short positive evidence supporting the
I made it.
existence of aliens. I'll certainly grant that. Elon Musk, he makes a good car, but he's kind of like an alien in a way. And this was
2030 it says up there.
2030, he
and,
was on Mars, and that's
and
his.
I made it.
Okay. I don't know how you
It's a
gentlemen
long
think.
time ago, according to this.
Okay, so we're way in the future on this. Back to the hamburger from hell with the tongue out. Okay, now, did you find that really?
What?
That didn't get that superimposed picture of Einstein. You didn't send that with the original. But you did send out another periodic table cartoon this morning. It'll be next week.
Yeah.
I won't give it away, but it was cute. It was funny. And puts us all in a silly mood here. Oh, incidentally, we're saying farewell to the Mars Ingenuity helicopter. I didn't get to that one. But light
Yeah.
cones from hell. Oh my God, we're going to get through that again. I hope there's no test on it, Jerry. Crazy. All right, what is this? I don't recall
This is
that.
an extra last minute picture I picked off from a lady in Bulgaria sent it to me. It's a very nice picture of sundogs
Mhm.
taken in Saskatoon, Canada. And my spell checker changed the title to Sunday instead of Sundog.
Oh.
AI still has uncharted territory to go.
Yeah, I was tent camped in the Arctic, 300 miles from the North Pole, and we saw this sort of stuff.
Yeah,
Mhm.
I think that's very nice.
Once again, it's atmosphere that does that, that turns the sun into three.
It's ice particles
Ice
and water
crystals.
particles in the air.
Yeah.
It was a really nice ring around the moon, not 2 nights ago.
Uh-huh.
Oh yeah.
Okay, the moon wouldn't be in this photograph, would it? Or this?
No, now
photograph?
we're back to what you got over the weekend.
Got it. Surface.
And we're just putting the planets in place. This
Got it.
picture shows Mercury, Mars, and Venus in the pre-dawn sky.
Mhm.
And as Bruce pointed out this morning, these star charts have to be blown up to see it okay. Right there at the fingertip, that's Venus
Mhm.
there. Over here is Mars, and
Mhm.
right next to it is Mercury.
Yeah.
So they were on I think it was the 27th.
27th, yeah, Saturday
Yeah,
morning.
they were less than a degree apart in conjunction.
Hmm.
So the only thing more dramatic than a conjunction of two planets is a collision of two planets. But that, so
I
this
mean, that
is
would really be something.
this is in the pre-dawn sky,
Yeah.
and
What are the green dots?
the green dots. These are various things. These are star clusters.
Mhm.
Oh, well, we certainly talk about them a lot.
But they haven't been
Yeah.
labeled.
No, they're not labeled.
Yeah.
I turned the label. This Sky software will show so much information on the screen that you literally can't find what you're looking for. So I turned most of it off.
Mhm.
Like Stellarium.
Yeah, they're competing with each other.
And those lines are supposed to represent a constellation?
These lines here, they are connecting in one person's opinion, they're connecting the stars to form for them the obvious asterism that represents the constellation. But in my view, Sky X does too many lines. And so
You
it
can
kind
see
of,
the teapot.
Mhm.
You're
well,
missing
yeah, you
one
can
step.
see the teapot, but all this other crap in there.
Yeah.
So, and this is the pre-dawn sky. This is a preview of what's going to come, because Sagittarius, that's this one down here. That's a summer constellation. It's in the evening in the summer.
Right.
It's the center of our galaxy is right up about here.
Oh,
More down and right, but
Yeah, down right. Yeah.
We're down to the right.
Yeah.
Oh, I
Yeah, the
always put
spout
it
of the
in
teapot.
it's
theme.
off the spout.
It's
Right.
what?
Right. Near El
Just off the
Nasi.
spout.
Right. Near El Nasi.
Yeah, off the spout.
Okay.
so that's where the unseen supermassive black hole would be.
It's not unseen anymore. We have pictures of it.
Well, you've never seen it in your scopes. Sorry, guys.
Well, our scopes are a little small.
Needs radio, doesn't it? Okay.
This is the evening sky. Locate two other of our planets. Neptune was so faint, I put a cursor around it up here on the chart. And then oh my goodness, what happened to
There's Saturn.
Saturn?
Yeah.
Right below your hand.
Yeah.
Oh yeah, there it is. Yeah.
Yeah. Very
It's the
low
white
now.
thing
Very
here.
low now.
It's the same color as this galaxy over here. So maybe that's Saturn. Same color. Yeah. Okay.
When do we lose the ring? When does it go flat on us?
I think a
March.
couple. What's that?
March of 2025.
Yeah.
Okay.
Another year.
That's going to be interesting. If some people don't get told, they won't know they're looking at Saturn, will they?
Well, the ring goes invisible for a rather short period of time, does it not?
That's what we're talking about.
It's
I
a
know.
couple of hours.
Yeah, exactly. It's exactly edge on, then you can't see it. because it's so thin.
So like how many amateur astronomers are going to say, hey, you want to see the planet with the rings? And nothing.
Well,
Yeah.
if they've been watching it, they'll be seeing the rings narrow. So
But you can see it as a line for a long time. Here we go. Oh God, are we into this already?
We're talking about dimensions here, just
And
getting
this
the
is gonna-
basics straight.
And
We
this is
kind
going to
of
go into
got off
light
track last week and started
Okay.
talking about things that we needed pictures for. So I drew a couple of real simple stick figures here. This is as you're going to guess, this is a rectangular solid, but no, this is a projection of a rectangular solid in 3 dimensions onto 2 dimensions. But you know what a rectangular solid is in 3 dimensions. You've handled them. You know, you've had blocks without letters on them and stuff, all sorts of things. So you know what a 3-dimensional object is that has corners and sides and edges. And so when you see this picture, it immediately tells you what it is. You know it. You're not confused. This is the same figure, but in 4 dimensions projected onto 2 dimensions. And so the original figure is right. There's the top part of it. There's this, then there's the bottom part of it, and there's the back sides. So that's in there. You take that figure and you displace it in any direction, and then you connect all the vertices like that. And that's the representation of a 4-dimensional cube onto a 2-dimensional surface. And in this case, it's a mathematical object that we use a lot called a tesseract. And it's used in science fiction movies a lot with mystical powers, but it doesn't have that. It's just a confounding of your mind because you've never held a 4-dimensional cube. And so you have no experience with what the shape means.
Yeah, I was going to say, Jerry, there's a beautiful explanation of this in a book I read as a kid by Isaac Asimov called 1, 2, 3 Infinity.
Oh yeah, read that.
Yeah, it's a really nice explanation.
Yeah. So do you remember the explanation?
There was a scientist named.
Well, he just had a basically a light source, with a naked cube, just projecting it onto a screen from different points of view.
Okay. You can make this as a mathematical construct. It's very easy. And then you can rotate it and you can watch what happens to this projection as this 4-dimensional cube rotates. And it's very, as it rotates about different axes, certain parts of it appear to go away or get smaller. Other parts get bigger as it comes close to you in 4 dimensions. But we have no personal experience with that. So it's just very confusing to us visually.
Well, can I tell you what's confusing to me? 4 dimensions means 3D plus time. Where is time involved?
No, we're getting to that. That's exactly why I made these charts. Now, this is 4 dimensions. And it's 4 spatial dimensions, X, Y, Z, and something else.
Q.
But they're all spatial dimensions. Now, the 4-dimensional world that we live in is 4-dimensional, but it's not 4 spatial dimensions. It's 3 spatial dimensions and time. And to make the units come out right, when we do these calculations on space-time, we always represent it as CT, that is speed of light times time. That gives it the units of dimension of space. So you can treat it as a 4 vector or a tensor, which just means it's a tensor, a vector, but in 4 dimensions. And this covariant thing is very simple too, but I'm not going to get into it.
And you're not going to get into the quantum stuff about 11 dimensions, right?
No, that's a whole different thing. There's physical evidence for 4 dimensions in space-time. No problem there. 11 dimensions is one of the projections of a hypothesis or of an unproven theory, a speculation called string theory.
And there are various ones. Some of them have 15 dimensions. Some of them have 23.
That's why I said it's just one of them.
Yeah.
But that's not reality. Those are mathematical constructs. There is no evidence to support those theories as being right. So Now in that, we're going to look at, this is a projection of 3 spatial dimensions. It's a coordinate system called a Cartesian coordinate system. It's X in this direction. This is 0. So it's positive X this way, positive Y this way, and positive Z, the 3rd dimension, up this way. If you take your fingers of your right hand, put them along X and curl them into Y, then your thumb will point along Z. So that's called a right-hand coordinate system. And that's what we normally use for Cartesian coordinates. Now, we're going to represent, we just represent time as time. So if you have a flash bulb that goes off here at time t equals 0 at the center, then at t equals 1, whatever units they are, the wavefront, that's that light, is out here, and twice the time later it's out here, twice the distance, roughly scaled, maybe not exactly the scale, but it's a freehand drawing. So you're sitting out here, you're not going to see that flash bulb goes off until this wavefront reaches you. It's traveling at the speed of light out toward you. Okay. So now with that in mind, we go to what's called a light cube and a light cone. And these were made up from discussions between Minkowski and Einstein to try and keep causality straight in people's minds. And they're neat diagrams. This is a diagram in what's called Minkowski space, which is where everything is flat. And in Minkowski space, because it's flat, that means there's no mass in the universe, nothing. Because if there were mass, space-time would be curved near the mass. So in free space out there, this is you, the observer, and your flash bulb goes off and the light goes, this is spatial dimension, X and Y, for example, and this is time. So this, as you go along this axis, your light front wave expands. And so if there's someone standing here, he's never going to see that light. He's got to come up. He's got to move along this axis until he runs into the light cone, and then he can see the flash from here. So this is future. This represents past.
Jerry, can I just mention something?
Go ahead, please.
Yeah, there's a really neat, not to say your explanation is not great, it is, but there's a book I've got from a friend for Christmas called Existential Physics. It's written by a woman, scientist, Sabine Hossenfelder, and she does a lot of YouTube stuff. She's really good. She's really good. And in one of the first chapters, she does a beautiful job, okay, of showing what you can't see and what you can see. So she attaches to this light cone concept. And until that point, I didn't realize that it was convention that decided that the light cone shape would be 45 degrees. So I guess people agreed, okay, scientists agreed that the light cone should be 45 degrees. Of course, that's what we use, right? But she did a great job. I just recommend the book, Existential Physics, Sabine Hossenfelder.
She's also on YouTube a lot.
Oh, yeah, she's good. You like
her? I'll look her up.
Yeah.
Hossenfelder? What's her last?
Hossenfelder.
Felders. Okay.
Yeah, like German for
Good German name.
Yeah,
Hossen means rabbit.
I don't understand past light cone. Does light come in or does it go into the past? Why do we have a cone on the bottom?
Well,
those
we'll
are
get to
things
that.
that could have influenced the event.
Yeah. So
If
this
the
light
event radiates uniformly in all directions, then you're going to have 2 light cones.
it doesn't radiate in all directions in this plot, because this is time. Like Tom was just pointing out, this angle here is 45 degrees from time and space, but that's only because these 2 axes, time and space, were dimensioned so that this results in an easy to see 45 degrees.
Right.
If you put it in dimensions that we're used to, like feet and inches, the light cone would be indistinguishable from time because light goes so fast. But we scale it here so that we can see the detail of the light cone. Now, what happens is that this flash bulb goes off, and this light cone then is the wavefront panning out or expanding out. And then this hypersurface, that just means a plane of the present, is moving up. You're on that, and this plane, the cone is fixed, but you're moving up through and you eventually, someone standing here at this point will rise up and they will intersect this cone, and then they can see the light bulb that went off so long ago.
How do they rise up?
What's that?
How
That's
do they
time.
rise up? I don't understand that.
Well, that's
This
time.
this is the observer, and as time passes, you're always moving up this line.
Right.
If you're
The coordinates are changing in space.
Tim, it's called these things are called your world lines, okay? And if you imagine, okay, that you're sitting right at the origin here, and I'm just going to take you up the time axis, okay, and you're not moving at all in spatial, you just go right up that timeline because your clock is ticking. When you start to move, you go off that timeline. Okay, so you have a slight angle or something, but nothing like the speed of light, nothing like that. So I'm kind of used to teaching this more in a two-dimensional aspect, but this is really cool.
It's very, very simple, but for some reason, it gives everybody, first time they encounter it, all sorts of crazy questions.
Yeah.
But like here, it says hypersurface of the present. Well, you can't freeze yourself in the present. Right now is the present, and right now is another present later on. So you're always moving in time. You can't stop.
Right.
So that's why this plane moves up. You're standing here, and time is passing. So you're going to hit this cone.
Oh, the plane moves up. Okay,
Yeah.
all right.
Yeah.
When you were saying that if you're standing right where your cursor is, you
Yeah.
said you will never see that light, and that suggests that there are parts of the universe we'll never see.
That's
that's
right.
what
That's exactly
That's
right.
exactly right, Tim. That's it.
Yeah.
Really?
But the thing is that you have to wait until, see, this is from events that happened so long ago that they're so far away that here we are right now, and we're not going to be able to see these things for another several billion years. Because that's part of the space that we can't see.
Yep.
So
Interesting.
it's very simple, but it's hard to think about it because we're not used to thinking about this way. And that
I've been sitting here with my jaw open.
Well, can I explain how I see it?
Okay.
The web is taking pictures of supposedly that are 13 billion light years old,
right.
and therefore they're getting this expanding. I'm looking at it as an expanding globe from distant galaxies. And is there enough light? Doesn't the light ever just eventually get so little that there's nothing there?
The light, as distance increases, the brightness of the light drops off as the inverse square.
In other words, the number of photons. They're still little things, aren't they?
Yeah.
They are, but they spread out so that after a
Right.
while, you're just getting hit by one photon.
Right.
Yeah, that's why they leave the camera on. And
That's right. That's right. They get dimmer and dimmer and dimmer.
And the expansion of space causes the wavelength to go into the infrared, and that's why it's looking in infrared.
Right. Right.
Way in the infrared.
Wow.
Now this is no longer.
Here you go, Tim.
This is what happens to space-time in the region of mass. Matter of fact, a heavy mass.
The black hole.
These surfaces here are the event horizon of a collapsing star. That is, as the star gets more and more massive and more dense, as it collapses, the event horizon is decreasing. The event horizon goes down now. Now it passed this pink layer, which is the region where now light cannot get out of it. So it goes down to where it's event horizon, and every object has an event horizon. The Earth has an event horizon. But because the Earth's mass and density are so low, it's way down inside. You're never going to find it. And it's just a mathematical construct anyway. You can't, get tangled up in the event horizon. It's not a real thing, but except that it goes dark. And then now inside the black hole, as time goes on, now of course, the black hole's event horizon just stays the same. Light can't get out. But the mass of the star has collapsed down. And because once it gets inside here, we have no idea what it actually does in here. It may hit, as stars collapse, they hit some incompressibility of the matter that won't let them collapse anymore. But inside here, there may be something else that won't let things collapse anymore. That's speculative. But if there is nothing that stops the collapse, then it goes down to a singularity. But that's just a mathematical convenience, and is, in my view, is probably not a real thing. But that's represented by the singularity here. And so this is the event horizon of a black hole. This is the event horizon of a collapsing star as it gets down.
Oh, okay.
So this is the star collapsing till it gets smaller than its event horizon. Here you see what happens. These are light cones represented out here in flat bins far enough away from the massive object that they're essentially in free space. They're away from the mass. As they get closer to the mass, they tip over. So
Because of the bending of space-time.
yes, because of the curving of space-time in the proximity to the mass.
So the axis is what's tilting?
Yes.
Okay.
I'm sorry, I missed what you call those yellow.
Those are light cones.
Oh, those are the cones. Oh, okay,
Yeah.
got it. Past and present, or past and future, right?
Yeah, past and future.
Past and future, yeah.
Time, space, and space on the upper left. Event horizon.
So now you know all that. You're ready to start tensor calculus and general relativity.
No, thank you. I got to get through these two.
Well, on the one hand, they say, the light can't leave, and
Yeah.
then Hawking comes along and calls it radiation, or what?
Well, that's not light. See,
Yeah, that's a different effect.
Okay, whatever. Woo! I feel relaxed, and now we're back to good old moon.
Right.
Jerry, you should go to the Goddard Space Flight Center visualization studio, because you can get a really photorealistic picture of the moon at any libration at any time. You just enter the date and time, and it'll be much more presentable than this image.
Hey, I resemble that.
I mean, this one, when you blow it up, it gets blurry and.
Yes, that's true. But this one has labels.
Yeah.
Right, but they're blurry.
I think you can get labels on the visualization studio too.
This is how it looked to me in the western.
Yeah, I'll give it a shot. But this is only to show roughly the phase.
Yeah.
And then this region in here, next to my favorite three craters.
Mm-hmm.
Is that Theophilus?
Ptolemaeus, Alphonsus, and whatever that is.
Oh yeah,
Arzakel.
Arzakel. But this one over here is what we're looking at because an amateur, Damien Peach, took this photograph with his telescope.
I think at this point we shouldn't call him an amateur.
Well, I don't know that the amateur doesn't mean anything derogatory to me.
Yeah, I know.
But
an amateur doesn't get paid, a professional does.
That's what, but professional astronomers get paid very little. So it's a fine line.
Well, where are we on the moon on this?
That's what I was just showing. That's why I showed you the other one. See, we are right here. Right there. And just outside of the field of view is Ptolemaeus.
Now, is the sword and the moon, is Rupus Recta, is that on the other side from this?
Yeah, that's over in the Mare.
Yeah.
Okay.
So anyway, I see Ptolemaeus is on the other side. He's flipped his image. So it's just a dramatic photograph. I had to capture this and put it up. And since it's visible on this part of the moon this week, I put it in there.
Yeah, it looks like it was done by a rover. I mean, it's amazing. Or a satellite.
It shows a lot of fine detail in here.
Yeah.
He's a master of this.
Well, gentlemen, I know we're not on the part of the moon that we're going to land Artemis on, but does anybody know the status? There's supposed to be 3 launches, and the second one was happening right about now, wasn't it? Or they got it postponed?
But they're postponing everything with the moon missions.
Really?
Yeah.
Was the second going to be an orbit of the moon with people on board?
Yes.
And nobody goes down, they just bring them back, I guess.
Yeah. They're not going to go down on the moon in the second Artemis 2. There is a who was that put it up there? The Japanese, the SLIM mission.
Yeah, that was Japanese.
That just landed on the moon and tipped over.
Yeah.
Oh,
Yeah.
The satellite is laying on its side or its back, it's upside down, but they have established communication with it.
Yeah.
And it is
Oh,
conducting experiments, even though it's upside down or
yeah.
sideways, whatever it is.
That's
I-
what you
I
call
didn't-
bad luck. That's
What's
bad
that?
luck. That's what you call bad luck.
Yes.
Yeah.
Well,
Um,
it,
so
the
it-
solar
landed,
panels.
it landed very precisely within like
Yes,
100
yes.
yards of where they were aiming.
Yes.
Yeah.
Yes.
Pinpoint.
But it fell over.
Yeah.
So when the first, about a week ago, when the first, or several days ago, when it first showed up, the picture showing it on its side, I thought it was photoshopped, because I thought, how could it take a picture of itself if it was damaged and on its side? But it turned out it released a rover, and the rover went away and turned around and took the picture of the
Yeah.
probe laying on its side.
I think it released a couple of small rovers
Yeah,
while it was still above the surface, and they landed separately.
right. And so maybe they're going to go over there and tip it over or something.
Yeah. Or at least
Find a
wipe off
tree
the
limb
solar
for
panel.
leverage.
Yeah.
Didn't the Apollo guys set a camera off to watch their blast off from the moon?
Yes, they did.
Yeah.
And that's, a lot of people claim that that was one of the reasons that it was fake.
And
Oh,
and they screwed up the first one, at least Apollo 11. They didn't account for the fact that there was this time lag, and so and they didn't pan the camera right, and so the LEM part takes off, and then the camera pans later, and you don't see anything.
Oh,
So they had to figure that out for the later missions.
well, if any Apollo had flipped over on its side like the Japanese, they probably might have been able to right it.
No,
those things, those suckers are heavy.
They're that, yeah, even on the moon,
Well,
They're
it's
not
1/6
as heavy,
of
but
the
they're
Earth's
still too
weight.
heavy for a person.
Yeah.
be like turning over a car down here on Earth, I guess, right? Wow.
That's what I was going to ask you, Jerry. Is what kind of force would it take to write that? And in the reduced gravity, it might be okay, but then it would have to be some kind of upward force, because otherwise there wouldn't be enough. Wouldn't be enough leverage.
yeah, but it still has mass, so you still
Yeah.
have to lift that much mass.
Still has
Yeah.
inertia too to get started.
Yeah.
All right, where are we now?
Okay, we are in the head end of Scorpius. So this
yeah.
is in the morning sky. There's a star ironically named a crab, but it's really a
crab.
scorpion.
Acrab.
Acrab, yeah.
Acrab, yeah.
Okay.
So this is showing because the moon is still a bright gibbous this week, so we're not focusing on a lot of faint fuzzies. There's a couple coming up, but this is near the bright star Antares, which is a bright red supergiant. And there are objects very near it. One of them is M4, right there in the bullseye, and that is a globular cluster. This is about 1 degree from Antares, as I recall. And this is a photograph of, not much contrast for some reason on this, but there's Antares. There's a small globular cluster. There's M4.
I never knew about that. You have it on that chart there. I think it was what was it, 6144?
Yeah, right there, 6144.
Yeah, and I didn't know that was there. I wonder, is that too close to Antares to see?
No.
It's visible.
Yeah.
Oh, that's neat.
Yeah. And look, in M4, you can see it's kind of a horizontal line going across. It's not quite horizontal, but it's tilted from like 3:30 to 10 a.m. There's kind of it looks like a brighter line within M4. Because of that,
Yes.
it's often called the cat's eye globular.
Oh, and there's the brightness right there.
Yeah.
Yeah,
Oh, okay.
yeah. So this is probably the easiest star hop find in the entire sky.
So upper right's a star, that's Antares. Lower left is a cluster.
This is the bright Messier object. This is a fainter NGC that Herschel found. And then this is the bright star Antares. It's white here and saturated, but it's actually an orange or red supergiant.
Wow. Okay, and the distant one is also a cluster. Or the one in the middle right.
Yeah, that's another globular.
Gotcha. Well, given
I
the
just formed somewhat of a right triangle to find M4. in Scorpio. It's not a real right triangle, but it is a triangle that's fairly easy.
Wow.
You mean between here and here?
Yep, that's it.
My scope has a wider field of view. If I get Antares in there, I can get this in
Yeah.
at low power.
Well, for the second Saturday star parties, we rarely go on areas like this. We're normally on the most popular and vivid.
No, we go after M4.
Yeah, this is a popular one. It's in the south, so it's behind the tower down there.
Yeah. And it's summertime.
Yeah, it's summertime. This is a summertime evening object.
But Antares is popular because there's different names. What it means is anti-Mars or something like
Rival
that.
of Mars. Yeah.
Yeah,
Rival
Ares is the word for Mars.
And that's ARES.
Yeah.
Right. Also, some people mess it up with the constellation ARIES, which is Aries the Ram.
Yep.
Oh.
And also that star is just, it just blows people away when you tell them how big it is.
But there's a gentleman's agreement on Saturday star parties that everybody does something different, right? Nobody has the same.
No.
Really?
I tried doing that years ago where I'd pass out a handout to everybody and it would have star maps for different objects. And I'd try to assign different objects to people. So not everybody was looking at the popular stuff and nobody paid any attention to it. So
that sounds like the club members I know.
Yep.
Well, if you were on a desert, instead of with all those trees around, you'd have a big, vaster sky to choose from, wouldn't you?
Yep.
Okay.
Yeah, there could be better skies.
I put my scope, the mount on the Sky Tour, and it chooses all the brighter stuff, and at the end of the evening when you only got a couple of people around, then you can really start to show them the night sky, all of it, or not all of it, but a lot of it.
You can bounce around more, yeah.
Okay. Interesting. Where are we here? Oh, Andromeda.
Yeah.
The Princess. And it's an M31, right?
Yes.
M31. They're not labeled by M numbers here, but this is the constellation of Andromeda. And this is the galaxy, the Andromeda galaxy, M31.
Right.
Which is NGC 224, for some reason presented as N. And here are two galaxies, dwarf galaxies, way up here in the sky. But these are dwarf galaxies that are orbiting the Andromeda galaxy. They are gravitationally connected.
Wow.
These two are close-in ones that are gravitationally connected. And this is what those two dwarf galaxies look like.
Oh. How dwarf are they? They're orbiting Andromeda, right?
They're orbiting Andromeda.
So they're coming at us too, in a way. It's like
Yes. Yeah, the whole crowd is coming.
Jerry, are those observable?
Yeah.
They're magnitude 9, so you'd need a nice sky.
Mm-hmm.
Oh, that'd be kind of cool to go and show those. I had no idea that they're orbiting Andromeda.
Yeah, I was too. I was surprised because they're really in the sky. They're almost 10 degrees away.
Yeah.
If you really want to blow yourself away, take a look at, if you've got a planetarium program that has all the latest moon discoveries around Jupiter, just project all those moon orbits onto the sky, and it's like a huge chunk of the sky.
Yeah.
But are these
project them onto Jupiter's sky or our sky?
Our sky.
Are these considered part of the local group, or do we have our own galaxy, our own satellite galaxies?
Both.
Well, okay, they're all part of the local group. Andromeda is part of the local group, right?
Yes.
Yeah.
It's not its own separate system. Okay.
It is its own separate system, and depending on how you define systems.
Yeah.
And Miroc that you had in that chart, that's one of the corner stars that I use for the Star Hawk. But the Miroc is an interesting little star. I think it's 404 is behind it.
Yeah. NGC
right down there, Miroc.
Yeah, the ghost of Miroc, right, Tim?
The ghost of Miroc. It's really difficult to pull out of there. You need
Right.
you kind of need a good sky that's way behind Muroc.
Yeah, I
If I
think
remember, if I remember correctly, Muroc is halfway between the Andromeda Galaxy and then down here, M33.
yes, yes, right. It splits them. That's right,
Yeah.
Jerry. Mhm.
Oh, okay.
Okay,
Wow.
moving on. Let's see what do we
Winter
got here.
hexagon. Ah, there it is. That's a hexagon. I've seen quartz
Now,
crystals.
This is moving up in the world from, you've heard of the summer triangle and the winter triangle. Well, this is the winter hexagon. Competition never quits. So it surrounds Orion up here from Capella to Aldebaran, Rigel, Sirius, the brightest star in the sky, Procyon, Pollux, and Castor, and then back to Capella.
Yeah, and Betelgeuse is kind of, you can look at as the center of it.
Right.
Yeah, right
Kind of
here.
looks like the center of a clock, huh?
Yeah.
Yeah.
Well, unfortunately, Pollux and Castor makes it more of a seven-sided rather than
Heptagon. Yeah, you'll hear hexagon, heptagon, winter circle, winter oval, all kinds of.
See, that's the astronomers I know too. You got a better name. Anyone comes up with anything, you got a one better.
This is starting to look like that box in 4 dimensions.
That's right. Yeah.
That's the winter tesseract.
Yeah.
Yeah, there you go. There's that. There's that. The thing that I use, Capella on the one side to tell you which star in Gemini is Castor. They both start with C, and then
close to Capella.
Pollux and Procyon, and that's the only way I can distinguish which is which.
Yeah, Castor looks more blue to me, and Pollux looks more yellow.
Yeah.
Oh, okay.
Hey, when we're at a
Castors are
star
multiple.
party and I forget which is near
Mhm.
whatever things else is, I just yell out to Chuck.
Yeah, exactly.
Hey, what else have we got?
largest digital astronomy scope camera you ever. There's a guy standing
Oh,
next to
my.
that lens.
Yeah, there's a person down here.
Good
This
Lord.
this glass across there is 1.3 meters. This is being assembled at the Stanford Linear Accelerator, National Laboratory in Stanford, Palo Alto.
Wow.
It's going to do the Legacy Survey of Space and Time, the LSST camera. It has 3,200 megapixels. That is 3.2 gigapixels.
Wow.
That's a lot of pixels.
Okay.
I originally thought it was 3 by 3 inch chips, but it's 3 by 3 chips together to form a raft, they call it. Each chip is about a little over an inch, about 1.5 inches across.
Wow.
Be a little difficult to hand hold that.
Yeah.
Yeah, you need a big neck strap on that.
Yeah.
And it takes forever to read out all the pixels, I bet.
No, it
Yeah,
actually goes pretty fast. They do, you don't read them out sequentially, you read out a
Parallel?
raft at a time. So they're all rafts are read out in parallel.
Okay.
And it's a 3 by 3 chip raft. So it doesn't take very long. They call it center taps. But it has 21 square, yeah, that's right. Let's see, where is it?
That is
It's
huge.
What?
That's huge.
Well, it's
It
3
is.
feet across. Yeah.
It's going to see first light in January 2025 at the Vera C. Rubin Observatory in Pachon Hill in northern Chile.
Mhm.
Don't you have a second picture?
Yeah,
Same thing, but a different angle coming up here.
Oh, wow.
Okay, now cameras on your telescopes are attached to the side, aren't they? They're little things, like your cell
that's if
phone.
you have a Newtonian reflector, you have to get out of the way of the mirror, yes. But for a lens, this one would be hooked on the back of the telescope because there's a hole in the primary lens. Like on these Celestrons, we have the Celestron 11 that you frequently see around, and the Meade 12 boat anchors. I'm sure Meade's a fine telescope, but anyway, those would hook onto the back of it. And the plane wave corrected Dal-Kirkhams. Now this shows the pattern. You're looking at the sensor, and these are the little rafts, 3x3 chips each one, and that's the sensor element back here. Now the sensor element, what's that?
Why the color difference in the middle?
I don't know.
I think it's reflecting whatever is behind the person taking the picture.
Could be.
Okay.
Which reminds me of something that there were two funny things. This is we have enough time for me to do a sidebar. Unfortunately, they executed a fellow with nitrogen gas, and
Right.
the press was very upset that what if this gas leaked out and people in the room accidentally breathed nitrogen gas. The news announcer was totally ignorant of the fact that our atmosphere is 70% nitrogen.
78%.
Already, whatever. And so, and hypoxia is probably the most gentle and easiest way to die, because you never know anything. None of your body system realize that you're going, because it only senses CO2. You don't produce any CO2 when you breathe nitrogen. So that was just absolute national ignorance. It was back there when they celebrated the change of the millennium from 1999 to 2000. The US gave proof that we can't count. So, and then the other thing, there was another one that struck me as odd, but, that's right. These UFO things, they show a picture of a UFO centered in a frame taken by an infrared camera. And it's this black object that looks like it's a little cross-sectional lens shape with something sticking up and down, and it's black and it's keeping up with the camera. That is probably the easiest UFO to debunk, because that's an infrared camera. And in order to operate that camera sensor, like the Vera Rubin sensor, it's not going to be infrared. This telescope is not infrared camera, it's visible. But for an infrared camera, it has to be cooled to about 80 Kelvin, which is minus 200 degrees. So in a picture taken by an infrared camera, a black object is cold. And that black object image there is about 80 degrees Kelvin. Well, there's nothing in this world that is going to be 80 degree Kelvin except the sensor focal plane. And so the sensor focal plane is taking a ghost image of itself. In infrared industry, we call that a narcissus, where the focal plane looks at itself by bouncing off a lens surface or some kind of a filter surface that was accidentally, because they don't do detailed scattered light measurements on many of these cameras. And so the thing is actually lying, so it gives an out of focus image of the focal plane. And that's exactly what they're looking at. And anyone who has worked with infrared cameras knows that that is nothing like a UFO. So anyway,
I counted these little squares up, and I think it's like about 16 across times 3 is 48 inches across at its widest point. Is that about right?
Right here?
Yeah, right. If you go right through the middle, I started counting them, and I come out with about eight, and then doubled it to 16 of those 16 3 inches wide across.
Yeah, it's about that size. I counted roughly really quick 15, but that sounds about right.
Yeah, so it's
Let's
like
see if
almost
I have
40.
a dimension here.
Well, can I ask a question? That center part where those pixels are, those squares, that's a glass lens that comes with most lenses, right? But it's not part of the telescope lens. It doesn't magnify. It simply clarifies the picture, doesn't it? It makes the picture form through the lens, through this camera that we're looking at.
This is a very wide field of view, and telescopes have trouble with wide fields of view. So you have to do a lot of correction. And that's what this is doing. This lens is really the final stage of an optical train that makes it all orthogonal. Oh God, I forgot the exact right word, but it preserves angles. There's no distortion in the image. So,
that's interesting.
or makes it orthoscopic so that angles are preserved.
Okay, but we all understand, I do anyway, that light comes into the front end of the telescope and hits the back end, which is a concave mirror.
Right.
And that's focused up, magnified to a receptor in the middle, right?
Yeah.
How does it get to this
It
thing?
goes up to a mirror in the middle that is convex. That is, it bulges out usually.
Okay.
And then that goes down through a hole in the center mirror. And then it comes to these lenses in the camera.
Oh.
It's a Cassegrain telescope.
Right. And it's a catadioptric telescope. That is, it has both lenses and mirrors.
Okay, is there a flat glass on the large circle, the outside that's closest
No.
to us here?
There's a nice graphic that I don't have here, but this has filters that are as big as this focal plane.
Okay.
And there's 4 or 5 of them located around the edges up here. And then there's with the edge of one filter, and then that filter will rotate out and completely cover this focal plane. Then they take a picture. And so it has a series of these things. So it does different regions from near ultraviolet to near infrared and across the spectrum. So it's like an expanded RGB red, green, blue image, which is what a sandwich do.
Wow, that's amazing.
But you're telling me the big scopes like this one would be on, go out the back end, but the scopes you guys use, they come out the side, don't they?
No, we use a Newtonian. Look at Chuck's. Well, Chuck usually brings a refractor, but sometimes he brings a catadioptric telescope where it comes out the back end. But
I do also.
Yeah.
Yeah.
What do they call that? False back? Something like that?
Okay, next week we're going to go over telescope types.
Yeah.
I didn't know that catadioptric means it's both lenses and mirrors. That was a new one to me, and that it really distinguishes between Cassegrain and catadioptric. I like that.
Yeah,
Well,
Schmidt
Cassegrain is a catadioptric.
Right.
And this is almost like a corrected Dow Kirkham then. This lens.
Well,
exactly.
Yeah.
It depends on what it's correcting.
And you know, they don't always come out at the top. You can have different arrangements for bringing the light out along the rotational axis and things like that. So
right.
It depends how many extra mirrors you want to stick in your system.
But this camera we're looking at right now, this lens would have no use at all on the web, right? That's a totally different. This is all optics here. Web is infrared.
But that's optics too. It's just different kind.
Well, how does it turn it into a picture and send it to us?
Through a lens. And it's to its sensor like this.
Yeah. This is just like your eye with the lens in the front and the retina in the back.
Well, all I see on the web is a big retina.
That's right. You're looking through the lens.
No, the mirror is not the sensor, Ron. The big folded up thing with hexagons.
Yeah, right.
It's the mirror. That's not the sensor.
So it's stuck out on the head of it in front, just like it's.
No, there's a secondary mirror up there, and then it brings it back through a hole into the back of the James Webb, and that's where these cameras get rotated in and out, depending on which one you want to look through.
Oh.
Turns it into pixels and sends them back to Earth in radio waves. Okay.
The big mirror on the web has got a black tower on it. And that's where the light ultimately goes in and gets processed.
Well, I wonder which pharmacy they take the pictures to be developed.
I think Costco's out of that business.
They're all out of that business, I'm pretty sure. It went the way of encyclopedias, didn't it? All right.
Okay, well, Ingenuity has been shut down.
Oh, no.
They broke a rotor.
Yeah.
They
did a hard landing and broke a rotor or something, just fatigued off.
But it got in a lot of work.
Yeah.
72 flights, 24 miles, no, meters high. about 70 feet, something, 17,000. I wrote down numbers and didn't tell what oh, there they are. They're on the
Yeah,
screen.
17,703 meters, total distance flown, 128 plus minutes, total flight duration. It landed on April 3rd, 2021, and it was turned off on January 18, 2024. It has reached an altitude of 24 meters and did a total of 72 flights.
Now, one of our drones that we have everywhere and on the Earth would not work up there, would it? It'd have to go super fast and it'd need two of them.
Yeah, the atmosphere is only 1/10 of Earth's atmosphere.
Wow.
Or 1/100th, isn't it?
Yeah.
So is it going to sit out there beside Perseverance, and Perseverance will look at it?
It's a pretty light structure. I imagine it'll be blown over.
Yeah. And it's quite far away, I think, from Perseverance.
And it would take pictures and send them to Perseverance, and then Perseverance would send them up to the orbiter, and then the orbiter would send it to us. Is that how it works?
Yep.
Amazing. What's the 128 minutes plus on the right side, upper right? What is
That's how
that?
long it was flying.
Right.
Oh, okay.
That's the time in the air.
Well, you did well, Ingenuity. Wish we could get it an award. Someday we'll check it out. Elon will check it out, won't he? In
There's a little
2030.
piece of the right flyer attached to it, too.
All right, listen, gentlemen, this Friday night, Dr. Tim Thompson, I think, who lives down at Mount Wilson, is going to talk about the observatory. It's been around for 100+ years. And then the following
Ron?
Saturday, anything else happening? Saturday is the
Quick
second.
question, Ron. Is Tim Thompson going to be Zoom or is he going to be in person?
He's going to be in person.
Okay, that's what I thought.
I
All
just
right.
sent an email to John Winkowski, our astronomy manager guy. Get in touch with him, tell him he's going to bring his laptop, and we're going to be in Fleischman Auditorium this Friday night.
Okay, good. I'll be there.
All right, good. I'm looking forward to it myself, and we'll do this for number 146 next Monday morning.
Okay.
That's it for the Astro Hour. Thank you, everybody. Thank you, gentlemen. Take care of yourselves and your wives. Don't catch COVID. We'll see you.
For now.